Muy buenos días tengan todas y todos ustedes. Es un placer, en particular para mí, volver a casa después de un año de ausencia sabática, justamente en la Universidad de Múnich, en Ludwig Maximilians Universität, donde tuve la oportunidad de trabajar en el departamento del profesor Don Dingwell. Él es una persona bastante, un investigador, un académico, un científico bastante reconocido en el nivel internacional. Eh, Realmente cuesta mucho trabajo resumir su currícula, así que voy a dar solamente algunas líneas muy rápidamente de su quehacer. Eh, uno de los aspectos que no incluí en la lista, pero antes de que se me olvide, debo mencionar que el profesor Dingwell es doctor honoris causa por nuestra universidad. Bien, el profesor Dingwell estudió su doctorado en la Universidad Simon Fraser en Alberta, en Canadá. Él entre el 84 y el 86 estuvo como Carnegie Fellow en el Laboratorio de Geofísica en Washington, en la institución Carnegie. Entre 86 y 87 fue profesor asistente en el Departamento de Ciencias de la Tierra en la Universidad de Toronto. Entre el 87 y 2000 fue investigador y subdirector en el Instituto Geológico de Baviera, Alemania. Después fue profesor visitante tanto en el Instituto Tecnológico de California y en la Universidad de Stanford. Una de sus posiciones más importantes, que son en parte un reconocimiento a su nivel académico y científico, es que entre 2011 y 2013 fue secretario general del Consejo de Investigación Europea. A nivel europeo tuvo ese gran cargo. Él fundó y fue y es actualmente director del Departamento de Ciencias Ambientales y de la Tierra en la Universidad de Múnich. No voy a mencionar todos los reconocimientos, solamente de los últimos años. Recibió la medalla Bowen de la American Geophysical Union, el premio de investigación avanzada del Consejo de Investigación Europea, la medalla Arthur Holmes de la Unión de Geociencias Europea, la conocemos más como EGU, la medalla Harry Hess de la American Geophysical Union, fue elegido miembro de la Royal Society, miembro correspondiente de la Academia Mexicana de Ciencias, de la cual ayer recibió un reconocimiento por parte del señor rector, el doctor Leonardo Lomelí, en el auditorio Alfonso Caso. También recibió la medalla Miller de la Sociedad Real de Canadá. También ha pertenecido a muchas y recibido reconocimientos de de la mesa ejecutiva de selección del Fondo de Excelencia de Investigación en Canadá. Y bueno, ha sido elegido miembro también externo de la Academia China de Ciencias, fue vicepresidente de la Academia Europea, pues de hecho, y también de la Sociedad Real de Edimburgo. Ha sido vicepresidente de la Academia Europea, presidente de la IABSEI, de la Asociación Internacional de Volcanología, presidente de la Unión Geocientífica Europea, de la EGU, y eh, ha publicado cerca de 560 artículos, para los cuales ha tenido más de 34,000 citas. Su factor H es de 94. Entonces, es un verdadero honor, un verdadero placer tenerlo aquí, científico de un nivel como el del profesor Dingwell, para hablarnos justamente de microlitas, bolitos y su impacto en los volcanes. Please, Don.
Yeah. Oh, hi, everybody. It's great to be back here. And I always feel like I'm coming home somehow when I come to you. I don't know why. But I also always nervous because I know the quality of minds that Unam has. And I will try to calm my nerves. Many talks here before, and I've this time chosen something a little different. It's an element of what we've done over decades. We visited it in different decades with different views, and it's become a very hot topic in the last 5 years. When you're in the game long enough, you will see that happen. You will write a paper, nobody will talk about it for 20, 25 years, and then suddenly everybody will talk about it. That's the wonderful nature of science. If you do something which is real and which is accurate, then it will find its value with time. And this is very different, of course, than in fields which are very hot. But in geoscience, and the topic is nanolites, a very strange thing. And I'll try to show you then where we came from with this, why we think today it's as important as ever, and perhaps also in places which you would not expect. So I'm still at the University of Munich for a little while longer, where I've been since 2000 there. And a lot of this research has been funded by this other thing, the European Research Council, which is the greatest thing that the European Commission ever did. So this is just to remind me to because everybody else is shouting Earth system, and so we have to shout it as well as volcanologists, that we are a fundamental element of the Earth system, that the Earth would be utterly different without volcanism, and so that even if you live a long way from an active volcano, you should give the respect to the volcanic processes that you give to sedimentation, that you give to ocean currents, that you give to atmospheric mixing. So I've been, and will continue to preach this in the coming years. I'm an educated audience here, so I won't waste much time with the front end of this contribution, but obviously it's a global problem. It influences everybody. You can use many examples of closed airports across the world, separated by thousands of kilometers of ocean, to make the point that it's everybody's problem when these volcanoes erupt, and you can use the statistics of people in the air to cement your case, and you can always point out that the spectacular number of ways to die in an eruption, this always gets everybody interested, no matter if they're a geologist or not, the spectacular nature of the hazards and the risk which is associated with them. And so what I'm going to talk to you about is completely experimental, because that's my life, and we are the poor cousins, we say in English, the poor cousins. We don't have much money, there's not many of us. Nobody notices us most of the time, but sometimes, and that's why I got into experimental work in the first place, sometimes if you're in the right place at the right time with the right idea of an experiment, you can have a massive influence on the field by what you can infer from the experiment, because it's a generalizable result if you've done the experiment well, if you've conceived of the experiment well. So there we are at the bottom where we belong. All the other people are up at the top, dominated of course by the field. And of course, everybody has felt the effect of numerical simulation in the previous decades. Many of you have heard me say this here before. So we have a fundamental problem in volcanology. We can only get so close. On the one hand, we have the advantage that we can see a lot that is happening. This is Stromboli from an old ridge above. Stromboli looks quite different right now. This is a couple years old. We can get this close in a small event scenario like this. Just close our eyes and make sure we don't get the ash, the glass in our eyes when it blows over. But we can't get any closer. So we can do all of the dynamics above, and we learn a lot about atmospheric acoustics and things like that, but we can't get inside of the delivery zone. We can't get inside of the conduit realistically right now. There are interesting ideas about how we might do this in the future, including drilling into the active magma, not waiting for the magma to come to us. But I won't talk about those today. So we have an access problem, and the basic response to the access problem is to recreate the volcano in the laboratory. And then you have all the access you want. Of course, we don't recreate the volcano. We say that we do in our grant proposals, but we really don't. It's impossible to create the complexity of the volcano. So we strip it down into what we think we can control. And again, this is the thing that somehow I learned as a teenager, how to do a good experiment. And you have to be able to build something that means that when you get the results, you can interpret them within a restricted range of variables, and therefore you can take one small step forward and then get ready to take the next step. So the basic idea presented here in German, I apologize, is that there's a sequential set of physical material changes that take place in any explosive volcanic eruption, from a saturation event with a volatile phase to nucleation and growth of crystals and bubbles, and eventually the development of a foam, which yields the pumice that we all know, and then a fragmentation at the top. Now, we don't believe anymore that this cartoon is correct. We think that there's a lot of overlapping between these processes, that you go up a little bit in this, and then you fall back, and you go up again, and you fall back. 2 steps forward, 1 step back kind of scenario in volcanic situations. And that this repetitive and stumbling, if you will, it's the first time I used the word for it, but this stumbling nature of some volcanic systems as they try to achieve their volcanic status, that this is a fundamental part of this, the signals that we get from monitoring these volcanoes. And of course, we are in the presence of Alejandra Arciniega here, who is working with our experiments and trying to understand all the signals that we're receiving acoustically from these experiments. So the key to the explosive event, as many of you will recall me already saying in previous talks, is this glass transition. You have to go from a liquid which is flowing and is just plumbing through the earth to something which is rock at the surface. And the amazing thing about the earth is the rock is often glass, which means it happened so quickly that it couldn't crystallize. It's as simple as that, that the crystallization rates were stolen or cheated from the system. So it was not allowed to build a proper rock, which would be crystalline, and you end up with all kinds of glassy remains of a terribly inefficient and incomplete system of rock formation, if you will. And the fine-grained range of these things contains what we call the ash below 2 millimeters in size. And ash has a overproportional impact in the Earth system because it goes everywhere, because of its transportability. It's just incredible. The finer it gets, the worse it is. And so it goes into your lungs, it goes into your jet engine turbines, it goes into the ocean, creates algal blooms, does everything. So if you ever want to argue with somebody that volcanism is critical for the Earth system, start with ash. It's very easy to convince them. Show them a 20-kilometer high ash cloud. Show them the global circulation of ash from low latitude eruptions, and then you have them. They cannot deny it, and they're probably even excited about it. So this is ash in transmitted light microscopy. It's just one example. You can see there are crystals which have been stripped of all of the original liquid which surrounded them. They were floating, they were buoyant in a liquid, and they were coming up. But now there's no glass around, so this is a very efficient process to actually process these to get crystal tufts to actually shatter the glass off of these things. But we also get these funny looking things that don't look like crystals. They're absolutely transparent. They have no crystallographic form. They're amorphous. They're without structure. That's the glass. And so you have a mixture of glass and crystals, more or less. And you also have bubbles inside of some of the glass. And over there you see a transmission electron microscope, a scanning electron microscope shot of fine pyroclasts, and you see I've taken the spectacular example of a woody or pumice, or just to demonstrate to people who have never seen ash before that the amount of surface that you have when you take these fine particles and throw them into a Earth system. If you look at it from the point of view of chemical kinetics and reactivity, where surface is everything, not mass, surface, then you realize you're doing the perfect storm, as we would say in English. You have a cocktail of gases which are reactive. You have very fine-grained material, high surface area, freshly produced, and it is porous as hell, so there's all kinds of room for reactivity. And in recent years, the biophysicists who are working on the origin of life mechanistically, they're all excited about doing it on rocks and doing it on very porous rocks for obvious reasons. That's another story, but just to let you know, that's a very active area of research, also in Munich, also with our research group. Yeah, and then you have the overriding property which is behind so much of what goes on in these systems, the viscosity. And the viscosity varies logarithmically as a function of temperature, water content, and chemistry. And this was something that inspired me at the very beginning of my career, still inspires me. We're still mapping this out. We have models which are intermediate models in terms of precision, but we're still measuring, trying to get the perfect model for how this one property, viscosity, varies as a function of chemistry, just as a function of chemistry. And I hope you can see that the effect of water here, which is in weight percent, upon ascent of magma and dehydration of the magma and formation of bubbles, you hit this catastrophe here, which is just before you get to the surface, pressure dependent, at a planet with 1 bar atmosphere, just before you get to the surface. And if you have a high silica liquid like this, you have to go through that catastrophe. And that, in essence, is one of the driving parameters of explosive reaction of magmas, because most magmas don't make it through that catastrophe without exploding. Now, I'm not going to show you field pictures of the volcanic eruptions, because you've seen more than I have in your life, and you live next to them. So if you walk into our labs, you see a material science lab, you shake your head and say, this is not geology. Well, this is the way it was when I was young. Yeah? So you had to be brave to go into this field and claim that it is geoscience, right? Brave or lucky. Lucky meaning you have a permanent job and you have good funding for a decade. Then you can do what you want. And I had this luck. When I was 28, I became a professor at Toronto, and then I was headhunted away to Germany with a new research institute, and that was what made the difference. That's why this whole field from my side was pushed. So here we can measure viscosity using material sciences. We have high viscosity measurements on the right and low viscosity measurements on the left. And we're often in the position where we have to combine data sets from these different techniques These, which have been specialized in solid state determination of properties like thermal expansion and so on, and these, which are very much liquid properties. But of course, if we do them in a relaxed manner, they're all liquid properties. There's no rigidity left in the system. And so you can map out the entire temperature dependence of a property such as the viscosity over a tremendous range of viscosity, over about 10 log units of viscosity. And I always used to say that this is perhaps the most variable thing in earth sciences, viscosity in volcanoes, with the one exception that I knew, which is electrical conductivity studies of the crust and mantle, which are even more variable. And then somebody in North Carolina mentioned to me a couple months ago that the permeability in hydraulic systems is also spectacularly variable. So it belongs to this class of properties where you're not interested in a 5% change. You may not even be interested in a 50% change, because the things which really dominate the system are 5 log units apart. So it's, if you have bad eyesight, it's a great place to work because it's huge effects. Okay, now I'm going to take you experimentally across that yellow line. There's 2 ways to do it, slow and fast. I'm not going to talk about slow today. I don't have the time, but I'll talk about fast experiments. And they're my tribute to my colleague, Mikhail Adedubirov, who is from Russia, who started this work with me in 1994. And we got our first Nature paper in 1996. We built this thing, which is our experimental volcano. This is the 3rd generation. Soon there will be a 4th generation in China with more instrumentation and sensors and lots of money to support it. But this one is the atmosphere in the form of this very large tank, which you call the capture tank, which just sits there and catches things, and which also takes, with ports, high-speed camera data and so on. And the magmatic chamber below, which you see glowing here, red hot to make the point. So about 1,000 degrees and 1,000 bars maximum here, hydrothermal bomb, okay? So we go from the magma chamber to the tank, and if we successfully, we would describe it as success, fragment the material, then we get what you see in the upper right, which is ash just made seconds ago, sitting on the bottom plate of this fragmentation device. All of this simply so that we can make ash. We don't have to spend a huge amount of money flying around the world looking for the perfect ash, which doesn't exist, of course. We can vary the properties of ash ourselves in the laboratory systematically. And this is a threshold of work in many fields of science which makes the difference. Sometimes a technology comes along, in this case a trivial technology for decompressing these samples sharply and therefore fragmenting them. And just the existence of that little experimental trick means you go from a world where you're archivally going around the world collecting ash, describing it beautifully as the way geologists always do, but where you don't have a systematic data set of ash. You simply have what nature has given you from any one volcano from 10 or 20 different eruptive events. In this, you can map out the space of ash properties based upon the physics which produce them. And that changes the questions that you can ask and moves your field forward. All right. You can see I'm old because I'm giving you these kind of philosophical perspectives, which is what happens when you get old. One of the good things that happens, I think, when you get old. Anyway, just a few demonstrations of what we've measured with this device. So we have here in this video, if it will run, I hope so, yes. This is what happens when we decompress the sample, and I think I've shown this in Mexico before. I apologize to all who have seen it before. But basically you have this uniaxial unloading, and you have the development of fragmented material, which goes all the way down to the ash fragmentation size. You can see it a little better in the next one. And there you see spectacularly, first the characteristic wavelength of the first shock as it goes through, and then these segments explode again, and then you have this beautiful, I was thinking, where's Alejandro? I was thinking about this picture when I was talking to you, or when you were talking to me yesterday. Well, so from image analysis, somebody needs to do a fluid dynamic analysis of that dusty gas. And then it all comes out the top, and of course, the difference between our work and everything that had gone before was we worked on real rocks, we worked on real magma. And a lot of people said, don't do it, you won't be able to fluid dynamically scale it. You're lost. You have to take a viscosity miles away from the actual volcano, otherwise you can't fluid dynamically get back to where you are in terms of the fluid dynamic constraints. But we're not primarily doing fluid dynamics. Here we're doing material properties, we're doing failure length scales. It's a different science. It took a long time to convince the other people who had previously been in experimental work using analog materials that it was at all valuable to put a rock in the machine. You know, they would look at me and think, well, he's a geologist, doesn't know any better, literally. We had to fight that prejudice for about a decade. But of course, if you put the actual material that is involved in the machine and you go to the actual temperature and pressure, you will see things that would otherwise not be seen. So there's your ballistic volcanian explosion, which I'm sure one of the other of you has seen before. And we can parameterize it. We have to come up with words to describe the different properties. This one is the threshold, which means the minimum delta P required to produce that ash, and it's a function of porosity. You have the whole world up there in terms of chemistry, yet they all lie on one line, more or less. And it just shows that it's physics here, not chemistry, which matters. And it's the porosity or the bubble content which gives the strength, tensile strength of the rock. Nobody is surprised to hear it when they hear it. And there's about a factor of 10 difference in the strength of a low porosity rock to a very high porosity one, in this case, glass-based. Huh? All right. The whole process is very slow. We know the acoustic velocities in these materials, and they're still up around kilometers per second. We're still dealing with rocks. But the actual drop of the fragmentation into the sample is about 10 to 100 times slower. So it's a very slow process of grinding through these materials. And these rates go so low that they actually come into the sphere that we estimate independently from petrology for the rates of supply of the magma to the fragmentation. And so right away you have, in principle, a way to argue for the continuous explosive eruption of a volcano over days or weeks. It can be that the destruction is equal in speed to the supply, like a chemical engineering way of thinking about things. All right, I'm going to jump a little bit ahead. I have to show you, and you all remember this if you've seen it, but I have to remind you, if you had not been working on rocks, and if you had not been working at the right temperature and the right pressure, and with the high-speed cameras, you would never have seen what comes next. And you already know from the left-hand side of the diagram what comes next is the near-vent lightning that we produce in the experiments, which we were not expecting, which we thought was a malfunction of the camera. But then it ends up being something which has led to a new ERC grant. It's led to antennae measuring the electrical field around volcanoes as a monitoring technique, and many other things. Spectacular accident. And that's the wonderful thing about experiments. Experiments allow you to have accidents. I think field work, I don't know, I'm looking at Hugo now. Let's talk about that later, whether you can have accidents in field work like this, where you stumble across something. I suppose you can find things you're not looking for. Surely that's parallel kind of argument. I think it's very difficult to have accidents in simulations. But I'm not a guy who does simulations, and I would love to have my thesis overturned. Yeah, so here we are, 1996. And thank goodness I was paying attention when I wrote the title of this paper, and I put the quotation marks around the nanolites. You know that means that you've created a new word, and you're just gently giving it to the audience and hoping that they will accept it, right? So microlites and nanolites, if you will. 1996, together with Tom Sharp, TEM expert, and Richard Stevenson, who was expert on alkaline rocks. And basically, what we determined back then was that we have the phenocrysts, we have the substantially sized crystals that you see that have been resident in the magma chamber, or have accidentally fallen in, various things. That's what a lot of petrology has been based on for a long, long time. And then you have the microlites, which are basically, you're going into the ground mass now and even finer, but we know that we have microlites, and we think that these microlites are related to the last events at all of crystallization just before these systems erupt. And then we discovered that looking at grain size distributions, painstaking work, looking at measuring the lengths of individual nanolites, we discovered that we have a grain size distribution envelope which is separate from the microlites. So it's not just small microlites. It's not just the tail end of the microlites. That's a very important point to make here. It's a separate event. Whether it's separate in time, I cannot say. I don't know that. But in its mechanistic expression, it must be distinct somehow from the microlite creating event, okay? And these guys, if they are happening in volcanic rocks, they must be happening, I mean, literally, we suspect as the thing erupts, because they're so fine-grained, or by annealing later on, as I'll mention in a moment. So they're very close to the action. They must be somehow. Sometimes they're there, sometimes they're not. That means that scientifically we have a really good question now. Why are they there when they are there? What does it depend on? And is it important for the material properties? Okay, and that's the rest of the talk basically. So, I have to take you through a couple of methods that we developed to help you to understand what I say next. We've taken glasses from this entire range of composition of natural materials, terrestrial natural glasses. There will be other ones on the other planets, of course. We already know from the moon. And then what we do is we heat them up and we measure their heat capacity in a calorimeter. And if you take a glass and you heat it up, and if it does not crystallize, then it will give you this. This peak is what we call the glass transition. It's the enthalpic expression of that golden or yellow curve that I showed you earlier, okay? And you have on the left-hand side a heat capacity which is relatively low at low temperature, and you have on the right-hand side the hint that the heat capacity is going to be much higher. And the reason it's much higher is because you have the liquid structure changing through configuration as it goes up in temperature, because the liquid has no lock on the structural state. The glass is frozen in its structural state, so it only has vibrational components to the heat capacity, but once you cross the glass transition, you have vibrational plus configurational. And that configurational change literally makes the difference between the left and right-hand side of the diagram. So the peak in the middle is what they call the glass transition in glass science. And it's very valuable because where it occurs is directly related to the viscosity. Because the viscosity is the inverse of the diffusivities in the liquid. And the diffusivities are what controls relaxation of structure and movement of atoms. It's what wakes up when you cross the glass transition. It's what makes a liquid able to flow rather than simply be compressed and elastic. It's the ability of the atoms to actually move out of the way during these deformation events. And so, what we have here is a plot of the logarithm of the viscosity as a function of temperature for various compositions here, as you can see. And here you have a plot of the same kind of, a different kind of data for the same samples. You can see these names here, but it's the, what are we plotting here? We're plotting, you've got to stare at it for a minute and listen to what I say. We're plotting the log of the cooling rate or the quench rate versus a temperature, but what temperature? It's the temperature where that peak occurs. And the observation that you have to make from left and right is the slope is the same. So what we're looking at is the same phenomenon of relaxation in the liquid, but we're looking at it with a viscometer and we're looking at it with a calorimeter. It means that if you have a calorimetric measurement, you can state a viscosity. And if you have a viscosity measurement, you can actually state a calorimetric response. That was something that nobody liked when we said it in the early 90s. Although the glass scientists knew it, everybody in geoscience said we were crazy. It's a normal part of what I'm trying to say to you with these offhand comments is just normal part of the process. You know you're getting somewhere when people think you're crazy in a long research career. And there you have them brought together. You have the two plots together, right? So you have the log of the cooling rate versus the peak temperature, and then you have the viscosity versus the temperature of measurement of viscosity. And you see that the two colors of symbols, they all fall together on that plot. So this is absolutely a very fundamental observation using two very different machines. Normally in the past, people who worked in viscometry labs would never talk to a calorimetry person, right? So it's not perfectly independent of composition. There's another level, a subtle added level of variability which depends upon composition. That's taken up in what we call the shift factor. Shift, we didn't call it, we took it from the literature. It had already been worked out for glasses. in synthetic systems. The shift factor literally means how much do I have to shift one of these curves to make it superimposed on the other. But it allows you, when you can calculate shift factor as a function of a compositional parameter, it allows you to predict the viscosity from a calorimetry trace or a calorimetric peak from a viscosity determination. So we used this, again, back in the 90s. That was my annus mirabilis, 1996, when everything suddenly makes sense. So here you see some spectacular examples of microlites. Yeah, you can see the scale in various obsidians of alkaline rocks. And it had always been very worrisome, I think. I look at Hugo and others, and I think probably this was people were well worried about the spectacular geometries that you're getting of these microlites now in volcanic glasses. And these, you could say, okay, this is some spectacular way that the nucleation event takes place, but maybe it's something else. Maybe it's cracks that have healed. Maybe the place where you can nucleate crystals is on a free surface with a hot gas next to it. And then it seals again and you don't see the surface anymore. Because how do you explain this? You have microlites which are lined up as if they're sheared out. Why aren't they homogeneous throughout the glass? What mess is this? I mean, your first reaction is either beautiful or really ugly, right? Because you can't explain it. So what we think in the meantime for all of these things is that these are things which have fragmented and healed, fragmented and healed. And when they've healed, there's been nucleation of, there's been a loss of pressure, there's been a loss of gas. Suddenly they jump to the side in terms of stability, and these microlites start to grow. And literally they heal so well, and this is the debate from the 1980s between Jonathan Fink and John Eichelberger. They heal so well that you cannot even see that they were fragmented. That was the issue back when they were fighting about the possibility of subterranean fragmentation. And this just goes to show that you have two kinds of data. You have the bulk measurement of the viscosity. So we take a cylinder of one of these materials and we just squeeze it and we get the bulk viscosity. But we don't know how much of that we should physically assign to the presence of crystals. All we have is a measurement of a composite material. And we don't have any calibration or standards that we can link it back to. And these things are so subtle in their variation that it's not a simple question of trying to separate the phases. I mean, try to separate these microlites from this glass. Anybody who's had a sample in their hands in the lab knows it's impossible. Huh? Or try to synthesize this chemistry of this glass so that you have a crystal-free sample, and then you can calibrate. It's also impossible because your slight errors in the chemical synthesis of the glass are going to be enough to swamp the difference in viscosity. So how can we say what the effect of these microlites is on viscosity? We use calorimetry. Because the bulk measurement of viscosity is a bulk measurement. It's crystals plus liquid. Whatever the relative contributions are, everything is being deformed macroscopically. So that's one value. Now I need a second way to measure viscosity where I'm only going to get the viscosity of one of the two phases in the glass with crystals. I'm going to get the viscosity of the glass or the liquid itself without any fluence of crystals. And how do I do it? I simply heat it up and measure its gas transition, because that gives me the viscosity, and the only thing contributing to the glass transition is the glass. The crystals just along for the ride. They're sitting there before the glass transition. They're sitting there after the glass transition. They don't interfere with the glass transition. So you're surgically extracting, through calorimetry, a measurement of one phase in a horribly two-phase material, and then you can compare it to the bulk two-phase viscosity, and the difference must be the influence of the crystals. I was so pleased with myself to have come up with this idea that we put out this first paper on it. And we showed that we get the same slopes through calorimetry and viscometry, and we showed that sometimes there's no difference. So this is Yerevan dry fountains in Armenia with microlites, and this is Yerevan dry fountains without microlites. And we could see that for many of the cases of these small amounts of microlites, we could not see the effect on viscosity. It's a subtle effect. I mean, it may look spectacular, but the volume fraction of the crystals is very low. Huh? And unfortunately, at the end of it, we tried to, of course, we did what anybody would do. We went back to Einstein-Roscoe and we tried to plot the effect of microlite concentration on viscosity. That was the whole idea of trying to do it in the first place, and we got a mess. We got this. Okay, so it didn't go anywhere. So it was a nice idea, but it didn't, like all new things, it starts with a nice idea, but of course then you have to get the precision down, you have to get the calibration down, you have to see if you can measure it better than the variation you expect to see. That's the fundamental aspect of any new measurement, right? So it froze there, and in 1996 I didn't go any further with this, okay? Now, in recent years, other scientists have come up with the idea that nanolite crystallization, which we believe can occur during the eruption, that this may suddenly switch the viscosity in the system, because if you have enough of it, it may have a physical influence on the viscosity of the system as a suspension of nanolites. The prime candidate is usually an iron-bearing phase. In this case, it's a hercinite, that's a spinel phase, right? Iron and aluminum. But we have also studies with iron oxides. And what you see there is a TEM shot. And this is 1 micron as the scale bar. So you see you're down in the nanolite range. We're way below 1 micron. And you see it's quite a volume fraction which is turning up there. This could have a physical effect on the viscosity. So imagine a system in eruption. Maybe you've sucked all the water out by decompression, bubble growth, fragmentation. The rest of the material is sitting there. The crystallization conditions that were inherent to it are gone because you've removed the water, you've changed the pressure. Suddenly it's jumped sideways with respect to its phase diagram, and it's perhaps undercooled by hundreds of degrees suddenly because the water left. And the water suppresses the liquidus, you see? And if it goes, the liquidus jumps back up again, right? So if you can create crystallization in these systems, then you might be able to see what the influence of crystallization is on the viscosity. So what we did here in a paper coordinated by Luis Pereira was actually a reanalysis of measurements that were 10 years old from Paris. And basically you have viscosity measurements of the system before, so they're nanolite free, and then the nanolites form, so before on the bottom and after on the top. So you have nanolite free, and then you just sinter the material. You force the crystallization of nanolites. Then you take a sample out again, stick it back in the viscometer and see what happened, and so on, and so on, and so on. And what we see is the viscosity rises generally with the creation of the nanolites. So the first thing a physicist will do is put up their hand and say, great, you've discovered the suspension effect of physical obstacles, inviscid particles inside of a multi-phase material. But we say, be careful, because it's still a relatively small fraction by melt. And what we've discovered by doing this kind of work is that it is a chemical effect of the crystallization of the iron-bearing nanolites, which is pushing the viscosity. Because if you take a few % of iron out of the bulk chemical composition of the liquid, silicon dioxide profits the most because it's 75% of the composition anyway, and it creeps up a few % in its concentration, and that pushes the viscosity up. So it's the chemical effect of the nucleation of these nanolites which is causing the bump in viscosity, and this, we presume, would be happening during eruption. So it could be that this is actually influencing variations in eruptive style, whether it occurs efficiently or whether it does not occur efficiently. It's an open question. We have to now look for examples where we think or suspect that it could be such an effect. This is the same thing with further data. In all the experiments, we measure a composition of a liquid at the beginning, we crystallize the nanolites, and we go up to another value of composition. We see what that composition is because we more or less quantitatively remove the iron from the liquid composition, and you could literally then go back into the lab and make that melt and measure its viscosity and check. And yeah, the statement is basically down here. Now let me show you where I think it's all going. This is another example of the same thing. In this case, it was oxide nanolites. It was Francisco Caceres from Chile who led this study. But the title tells you the whole story. It's the same thing in black, so to speak. These two papers, one based on 10-year-old data from Paris, which we discovered while we were doing the new data. And we said, oh my God, let's do that data as well. And it's a separate set of viscosity measurements, so we made a separate paper out of it with separate co-authors, of course. And you see oxide nanolitization induced melt iron extraction, it's a lot of words to what we mean, causes viscosity jumps and enhanced so he's bold enough to say, I think this was a geology paper, causes enhanced explosivity in silicic magma. Because if you can push your viscosity up, the propensity for explosions goes up with it. Now I'm going to jump ahead a little bit. We've been working for years on what volcanic ash can potentially do in the Earth system. This is one of the ugliest diagrams I've ever seen. It was preceded by another one by Alan Roebuck, which was even uglier, which was atmospheric effects of ash clouds. Blame Pierre Delmel and Paul Iris for this, but it's a generation of work waiting, which is the understanding of what volcanic ash does in the Earth system, from soil to the ocean to your lungs, to jet turbines. I mean, you can't think of a more spectacular collection of things that something can be responsible for. So we've been pounding away at trying to understand what the very nature of ash is. Is it simply broken magma? And depending on who you are and what your inspiration is, the answer is good news or bad news. It's not simply broken magma. It's broken magma that has been cooked in hot gas before you get it out of the volcanic vent. And how much it's been cooked and how long it was in the vent, we think is an important variable, for example, in the release of sulfur during volcanic eruptions. This is very exciting work from this year. We're trying to say that missing sulfur signals from certain eruptions are because the sulfur gets baked back onto the surface of the ash in certain chemistries of eruptions and in certain depths of fragmentation in the conduit, where you have 100 seconds or something like that to cook the material back onto the ash at high temperature. This is a machine that Ana Casas from here, this part of the world, used to do these experiments and to study the kinetics of the reaction between ash and gas. And this is a tumbler, which basically allows you to do ash-gas reactions in a reproducible and quantitative way. And this is the kind of surface that we produce in these experiments. This is a rhyolite, this is a dacite, and you see their surfaces are coated with sulfate crystals. And the sulfate crystals are the sulfur that you do not see going into the atmospheric effect of the eruption. So we think, for example, that Tambora might have been a spectacular example of this, where the chemistry and the depth of the eruption might have led to its sequestration of sulfur. I'm going to jump over a few more slides because my time is slowly coming to an end. So we go away from this simple idea, complicated enough, simple idea of the physical variation of ash, and then we go to Hunga Tonga. And what happened at Hunga Tonga? You all know, I'm sure, better than I do. We all watched it happen. We had pressure waves that ran around the globe. It was a little bit like Krakatau. I've seen myself the treatise that was written in Cambridge or wherever it was on the pressure waves from Krakatau. They literally figured out after the fact what these things were. It happened again with Hunga Tonga. People talked about the ocean of the Atlantic being noticeably hit by the pressure. But this is what it produced. This, believe it or not, underneath all of those salts that literally encrust, as we would say in English, encrust ash particles. So these are ash particles scooped up right next to that eruption. So that eruption was submarine. You figured it out by now. It was a few hundred meters depth. I don't remember, 800 meters or so. It basically took the lithosphere, shot glass particles into the hydrosphere, boiled the seawater, took these hydrosphere particles, send them into the atmosphere. That is Earth system science. And it can stand up to any other person saying that their work is more important for the Earth system. So you have the whole cookbook here, the kitchen sink, as we would say in English. You have bromides, sulfides, sulfates, chlorides, everything that you can possibly imagine in this one eruption. So when we worry about ash in the atmosphere, we have to worry about more than simply breaking glass and crystals. We have to worry about all the stuff that happens afterwards, all the stuff that gets baked onto the side of it. What is a primary ash? A primary ash has junk on the outside, I would say, crystalline crusts. And this influences ice nucleation, which influences weather, which influences electrical events in the upper atmosphere. It's all related, and no meteorologist is worrying about this. It's our job. I've literally been in meetings in Brussels where they're trying to get money after the eruption in Iceland. yeah, of Eyjafjallajökull, and the meteorologists from the Met Office, the great Met Office in Reading in the UK. I mean, gods, you know, these people had the entire European meteorological facility until they decided to leave Europe. And they literally stood up to me and said, yes, but Mr. Dingwell, it's all dirt, isn't it? I've literally, I mean, I wish I had my iPhone on at the time. Huh? So this is what you're up against when you're up against well-funded fields which think that they have daily responsibility for weather and stuff, and you guys are just playing. Maybe it will erupt, maybe it won't. Give them some money, keep them quiet. Now, this is the way that science politics works at a high level, unfortunately. So let's leave the Earth. Let's finish it off. Because just when you thought it was all natural science and cool stuff, but where's the application? Maybe there is. So, as you know, we're all going back to the moon. This is a slide I made. You can guess what country I was giving this talk in. This is the Chang'e lander on the far side of the moon. And we know that we already think that they've discovered chemistries of rocks which are different than anything we expected from Apollo. So yes, we are going to map the moon. We are literally going to map another planet. Within the lifetime of many of you people here, there will be a 10,000-fold increase in the data that we have from the moon. And in order to do that, you have to go up there and stay up there for a while. And so you have to create a moon base. So there's going to be a Chinese base, there's going to be an American base, there's going to be other bases. You know, it's real science fiction here now. And they're all going to go up there and have to engineer, and I've used the word for the first time, I think, the surface of the moon for their purposes. And the one thing that is for sure is that they're going to use local materials, right? So if you think that, you know, Carlos Slim needs to use local materials for making concrete, which he does, when you go to the moon, you're definitely not taking the building materials with you. So what is the local material they're going to use? First of all, 4 things that they think that they want to do for sure. They want to get oxygen out of the rocks. It sounds bizarre, but if you heat a rock up, you get oxygen out. We already know, because the redox thermodynamics of silicate melts are such that they auto-reduce with temperature. They literally emit oxygen. And if they have a significant amount of iron or titanium or something which is redox sensitive, then they will produce oxygen as you heat them up. It's just the way the thermodynamics go. Okay? So they're going to get oxygen from these rocks. They're going to get water from rocks. Even with the small amount of water which has been discovered in volcanic glasses, if you have a whole planet to work with, you don't have too many environmental constraints. So there's a lot of water. And of course, there's the idea of helium-3 mining, making it all worthwhile. The idea that there's helium-3 due to solar radiation of the surface of the moon, cranking up the amount of helium-3 that you can get out of these rocks. And I jumped over it, structural materials. If you're going to build something on the moon, you had to build it out of something. It's local materials, and nothing is more local than the lunar regolith. Now, regolith, I guess, is a word that comes from soil science, something that I might have encountered once in my education. But the lunar regolith, of course, is not a soil like we know it on Earth. There's nothing biological in it, as far as we know. But nevertheless, that's the word which is used to describe it, the regolith. And the regolith is fine powder which is covering the entire surface of the moon. And it is the accumulation of the entire geological history of the moon where you're standing. And one of the biggest geological events on the moon, first, of course, the dichotomy of the moon's crust, half lunar highland, half Mare basalt. That's essential because the Mare basalts are basaltic. They have 42% silica or something. The lunar highlands have maybe 10% more silica. And we're getting to it now. It's all relevant for the engineering because what we're going to do with it. But also, these lunar soils, they're made up of, well, let's call them regoliths again. These lunar regoliths are made up of the accumulation of volcanic events which have sort of rained down pyroclasts, a couple billion years ago. Impact events which have thrown molten and broken materials from the side on top of the volcanic glass. Irradiation events which are messing up the mineral structures which are exposed to the intense radiation of the sun. And it's very reduced, and it's so reduced, if you look at the right-hand side first, you actually have metal globules in the basalts. So we don't generally have this on Earth, okay? We're a little more oxidized on Earth. On the left, and you might all have been staring on the left when I asked you to look to the right, I would understand it. That's the famous orange and green glass from the last moon mission from Harrison Smith, where he literally just put his shovel in the ground somewhere and said, oh, that's interesting, let's take some of that. And it turned out to be a dichotomy of two different chemistries of glass, titanium giving the orange color in its reduced state and the green glass due to iron 2+. On the moon, the surface, and I have to go to a meeting on glass next week in Korea. And why am I doing it? Because I want to tell them that the surface of the moon has up to 25% glass, depending on where you are. Something like 10 to 25% glass. Now, as somebody who's fascinated by glass, that's enough of a reason to be excited. But there's another reason to be excited. And that is, how are we going to engineer the surface of the moon? And the basic idea is you've got energy, you've got solar energy, you are going to heat things up and try to make building materials. The alternative idea, which is still kicking around, is everybody's going to live in a lava tube somewhere where nature already made the roof. But of course, they're also collapsed lava tubes on the moon spectacularly. So if it's likely that we're going to engineer it, and the engineering is already kicked off in this direction now. I'm working with a group in the Free University in Berlin. And there's two basic ideas which are written here. Number one is very high temperature 3D printing, as they call it. You know, 3D printing means everything and nothing. But basically the idea is you melt the rock. So it's all coming home now. All the work of decades on what the hell happens when you melt rocks, on exactly what their properties are when you melt them, is suddenly there. And somebody walks in your door and says, excuse me, I have a problem. It's very exciting. Anyway, 3D printing, the idea is that you will melt them to a low enough viscosity that they will flow through devices which will allow you to, just like with plastic, to literally 3D build any structure that you need. Okay? The alternative, it takes a lot of energy because you're going to have to go to 1600 degrees Celsius to get the viscosity low enough. And imagine if something goes wrong on the moon. I can tell you what it looks like when something goes wrong in Munich. Yeah, and it shuts down the lab for a week. Imagine in the moon, yeah? And you also, once you've produced it at high temperature, you have to come down hundreds and hundreds and hundreds and hundreds of degrees before it's a solid. So what's going to happen on the way down? Maybe nanolites are going to happen on the way down, okay? So bear with me for a minute. The other way to do it is sintering, which means you just heat it up enough that it can slowly begin to stick together. That's Don Dingwell's version of sintering, okay? So from particulate material, you get solid material, okay? This is how all ceramics are produced. Huh? You only have to go to half the temperature, maximum, maybe even less, so a lot less heat. And what is the best thing you can have if you want to reduce the temperature of sintering? Glass. And it's there. It's 10 to 25% of the rock already. It's almost like God gave us what we need here, you know? The glass is what allows itself to be softened and to therefore deform and come into contact with the other phases in the lunar regolith and make a solid. And if you had to heat it up to the point where recrystallization has to do it, or whether you heat it up and it comes down and has to crystallize, it would take much longer and be much more difficult. So the presence of sintering, of glass in a sintering process, drops the temperature fantastically where you have to start. You're down around 600 degrees Celsius versus 1600 degrees Celsius. And in a sintering experiment, the amount of strain that you're talking about, and therefore things that can go wrong because you're juggling stuff which is hot, is tiny, because the amount of strain in sintering is mesoscopic. You can't even see it from the outside. Yeah, the brick gets a little smaller. Whereas if you're pouring liquid from 1600 degrees C, that's all, everywhere where there's strain in hot materials, something can go wrong. So you see already, I'm a big fan of sintering, although I love to melt rocks. And they may melt them for other reasons, oxygen, water, and all these other things. So there we are, we're on the threshold of all of this. People are working with analog materials for the lunar regolith. There's a whole catalog of these materials. Now every country has their own lunar regolith analogs. Even Germany has its lunar regolith analogs in test facilities. China has them as well. And even companies in the United States, of course, doing it the American way, are selling lunar regolith, classes of lunar regolith analogs. So what about the nanolites? And then I'm basically done, and I've taken up enough of your time. We know that if we heat, this is old studies that we did for a completely different topic, which was to understand the cooling history of rocks, of glassy rocks, by reheating them and looking at the hysteresis when they go through the glass transition. There's the glass transition peak, the largest one we ever saw. It's for a Mare Island pantellurite. This thing will never crystallize. You can abuse it all day long. It will never crystallize. It's a very good glass former. And it's certainly formed a nice glass. And then you can go way out into the liquid regime here, play around with it, sit there, cool it down, go up and down, do whatever you want. It's come back. It's going to be the same glass that you sent up. It's a good glass former because it has high silica and extra alkalis. I hope you can see that this is a really lousy glass former. The noise alone in the signals, and then we cut the data off at this peak is the same physics as that peak, but we stop the experiment as soon as we get there. Why? Because here it collapses into crystallization, which must begin with nanolites. So this is a basalt. This is the lunar mare right here. And if you go up above the glass transition, if you're trying to sinter here, maybe you can get away with it, but if you go into a liquid regime where you think that you're going to manipulate it, then you're going to go through a phase of recrystallization, and it's going to start with nanolites. Because this is why we need to understand it better for lunar compositions, a huge research opportunity for an engineering goal coming up on the horizon. And on this other side, this is the highlands. This is the analog for the highlands. There you have no problem, I suspect, of crystallizing nanolites by reheating rocks to do lunar engineering. What will the effect of nanolites be? If they kickstart crystallization, it could make all the difference in whether this material will hold together or whether it will collapse as a particulate mass because the crystals freshly formed don't want to stick to each other. And from all of my experience in the lab of seeing what crystallizes and what doesn't crystallize when I cool it down in the lab, I can tell you it makes a big difference how much iron you have in your rocks. And in the moon, everything is iron rich, which is going to push it. The Mare basalts are iron rich, which is going to push it towards nanolitization. And that's going to be a whole another area of understanding the kinetics of sintering than rocks which maintain their glassy fraction. All right. So we've been trying to this is, I think, the last slide of data. We've been trying to quantify it. How? The first thing was just a shout to the engineering community to say, it matters where you are on the moon because you're digging here. You're not going anywhere else. So choosing the landing site, which is now happening and has happened for I think the Americans have chosen all their landing sites now. They're going to go up. They're going to have to go up there, take samples, come back, and we're going to have to take each lunar landing site sample apart and understand how to optimize engineering for it. Right? You can imagine that that's going to be a loop before they really start choosing technologies, even. Yeah? And this is just an example of the viscosities versus reciprocal temperature of different lunar landing site candidate materials, and it just shows that it looks perhaps not like a large range of viscosity, but it is. It's almost 2 log units of viscosity, depending on if you're landing in the Chang'e landing site or if you're going back to one of the old Apollo landing sites in the Mare basalts. So it matters where you are. Literally, the half of the moon that you choose is going to determine which technology you're going to use to make high temperature building materials on the moon. And we've said it before the engineers have said it because, of course, they're sweating the engineering. It's enough. But, of course, we're the geologists. And who else is going to tell them? And who else is going to indicate to them what the sensitive aspects of the geology are? We have to do it. It's a glorious opportunity for us to be involved in all of this as it comes down the road. That's it. I'm going to stop there. For inspiration, I'll put up a slide of exoplanets. We'll never go there, unfortunately, but we now know that there are thousands and thousands of rocky planets. It's Star Trek, you know, but we can't go there. And modeling of these planets, of course. I mean, I don't know, probably all of you have read some popular scientific article talking about some exoplanet, and the questions that come up already beginning to bend our minds as geologists, where we're completely dominated by the geological history of the Earth and a little bit of the moon, and speculation about Mars and Venus. That's our world, right? But now they're coming up with things of these planets which are completely unknown to us in the modern state of these planets. For example, magma planets, lava planets. And they think there are loads of these planets who are literally in the state of a magma ocean. And the information they get from the exoplanets is the atmospheres, because they get it through the occultation of spectroscopic signals as it comes from the sun through the atmosphere of the planet. And these atmospheres are degassing, and they come to us and say, you understand volcanic degassing. Please help us to understand what these signals mean. And of course, there's a huge gap between us at the moment. Yeah? But it's also another area where the conversations that are going to arise from the things that they think they have to infer from the temperature of the surface of these planets and stuff, which are going to bend our minds to new ways of thinking about how planets are formed, just like Apollo did when we started talking about magma oceans in the first place back in the 1970s. So that's maybe a nice place to stop. Thanks very much.
Okay. Bueno, thanks a lot for this very interesting talk, taking us to from earth to heaven, if I can say it, or hell. But it was really interesting how these kind of studies can take us into a open door to opportunities in pushing earth sciences to some other level. Some questions?
If you used an andesitic glass that has higher iron, how do you think the results would shift?
Pascal Richet once said to me, I'll never work on iron-bearing glasses. That wasn't very helpful. But his reason was that he had this terrible experience of iron oxide crystallization because he was always doing viscosity measurements in the metastable state well below the liquidus. He was always in danger of incipient crystallization. And he said, whenever we do these andesite measurements, they just go sideways, and we know we're losing it to microcrystallization. So the general case would be that it's strongly dependent on the iron content, the same as in rhyolites. We have rhyolites with a few weight % of iron in Iceland, right? And we have rhyolites with a few tenths of a weight % of iron. And that likely makes all the difference. It's the iron-rich ones which are susceptible to what we used to call mineralization. You know, one of the first papers I worked on fluorine in my PhD. One of the first papers I got was from the slag, steel-making slags, and it was the mineralizing effect of fluorine. And what they meant was, of course, the fluxing effect and the growth of crystals chemically and physically by dropping the viscosity. So I guess it's going to be the mineralizing effect of iron, which is going to be the big determinant in how an andesite responds, and that means it might respond one way or it might respond the other depending on the andesite you're looking at. It's another sign of old age that your answers get longer and longer.
It's really interesting to talk about the role sulfur dioxide is taking a role in all these processes. Sometimes we see at volcanoes that SO2 emissions are increasing, coming down, and there are several ideas, perhaps the rate of degassing, the amount of gas involved in the magma. But now, thinking about this kitchen where SO2 and fragmentation are being cooked, what other processes might be happening for producing these variations in SO2 emissions?
Yeah, up to now, we've just been thinking about eruption A, eruption B, eruption C. We know the chemistry of the glass. We think we can estimate the fragmentation depth. That's always a big question, of course, because it's the fragmentation depth, meaning the depth from the decompression that takes place at the crater, which will give you the transit length and therefore the transit time before the system drastically cools and then it's just shut off. So the big crunch is to know how deep the fragmentation is likely to take place. This is a very interesting question to be posed. But I've never thought about it. You just made me think about it in a new way, which is, could one look at an active series or ongoing event, look at variations in the actual sulfur coming out longitudinally, as the social scientists say, with time, and at the same time try to pluck something else out of the signals of monitoring, which could be used to infer whether there's variations in the water in the well, so to speak. That's interesting. I never thought about that before. But if you had something from acoustics or from seismicity or something else which could tell you that as the eruption evolved, the fragmentation front moved, and you can reasonably argue, and if you could correlate that with sulfur, wow. I mean, if you came out there with a first order correlation one way or the other, then we're in business.
Or perhaps trying to study a little bit more the coating film that is absorbed in the ash particles. Yes. Por ahí anda Benedetto. Something interesting for you. Another question?
How much nanolites in terms of max fraction do you need to create these jumps in viscosity? And if this fraction of nanolites could affect other properties of MAPA, like permeability, for example, or create surfaces for nucleation of bubbles that could also affect the fragmentation level. How could this influence could reflect in the whole magma column and the explosivity of the eruption?
So I think the short answer, coming from the back of your question to the front, is yes. There's one paper that really got this sort of discussion kicked off, which was a Japanese paper. I've forgotten the authors. Maybe some of you remember them, which claimed that they saw a difference in eruptive style based upon, I think it was on nanolite to microlite populations. I would expect that a wide variety of properties are influenced by it. One of them, the toughness, the fracture toughness of the material. I mean, microcrystallization is one of the things that ceramicists know very, very well, influences the toughness of the products that they make. Yeah? Anything which produces internal surfaces will certainly change the reactivity of the material once it comes out of the volcano. Yeah? In terms of how much you need to see a noticeable effect, the cases that I showed you were for a few weight % of iron oxide. If you take that much out, and if you go from 72 to 75% silica, that's enough that you can clearly, because that starts to get up the steep end of the curve in terms of the effect of silica on viscosity, and that takes you where you could change the viscosity by 50% or by 100%. And that, again, that sounds like I said earlier, that's a small number. Most people measuring viscosity are not excited about that. But I will quote Jan Bottinga, the famous silicate melt chemist who is unfortunately no longer with us, but he said, you know, people always say, who cares if it's 50% more or less viscous, he said, but if you're on the Autobahn and you're driving twice as fast as the other guy, because basically the strain rate that you have is twice as much as his, well, that's the changes in strain rate you will see if you have heterogeneity in a flow due to viscosity shifts. So in terms of what happens to the flow itself, which will then precondition the physical properties of when it's deposited, it can be quite a significant event, even a 50% change in viscosity. Yeah? I mean, when we started that, we said it could be a physical effect of the suspension. When we reached the conclusion that it wasn't, that's just the next step in understanding the system. Now we have to go further and understand, can we then nevertheless see somewhere, somehow, the physical effect of the presence of the suspension on the properties of the system? And that's what I think you were asking. Yeah. So we wouldn't expect to see it in iron-poor calc-alkaline rhyolites, the ones where you're struggling to get 0.5% of iron in them, right? So these typical Western North American rhyolites, which are typically very iron-poor. Yeah. But in Iceland, where you have a few, where they're like tholeiitic rhyolites, then you have a lot of iron in them. And there is where we think that it could be quite important. And on the moon, you have more iron, of course. So all of these things potentially multiply when you go to the moon. And you have titanium reduced. We don't know anything about what that does to the properties of rocks.
Thank you, Professor, for your very nice talk. As you know, I do fluid dynamics, and I was wondering, these eruptions are very complex processes, of course, but I see two main reasons for it. It's complex from the rheological point of view, for one thing, and the other thing is because it's a multi-phase flow, essentially, right? So my question is, which of these two factors would you say is more relevant to the eruptive process?
And my answer will be, it depends. Clearly, if you're foaming these flows, then that becomes eventually a dominant effect on how the material is going to respond, because eventually you get rigidity in the foam, and then everything changes. You can't push it, right? And we see that, and that's been modeled by Jopard and others in Paris, what the distribution of stress, of the viscous stress would be within a foamed extruding flow, and how it would vary radially and so on. So models have been begun on that front, yeah? But in terms of chemistry, chemistry is basically preconditioning the source of the material which is going to lead to volcanism. So the chemistry is extremely important early. Later, the physics takes over. But what we're learning is that you can't forget the chemistry, because the nanolites will be controlled by the chemistry again, the damn things. And so just when you thought you were safe, chemistry comes back to bite you. And we don't know where we can now draw that perforation between physics and chemistry and the variability of eruptive processes. It's been thrown open again by this question, I think.
Well, this was a very interesting talk for everyone to see that we are normally, as volcanologists, seeing the big picture, the large events, the columns and things like that. But in the microscopic world, there is a key for understanding many things and taking us to discover and conquer the space. There is many people starting to dream about going to Jupiter, Mars, and having a station on the moon. As you mentioned, it's needed this kind of knowledge. The question here is, how far are we to those plans, according to what you see?
You mean, how far are we from understanding those processes? Oh, I think young people here will see it. I think you will see it. And there's going to be terrible mistakes made. I promise you, because it's just the way it is. You know, there's trial and error. And maybe one or the other of those mistakes will be due to something you heard today, and you'll say, you know, way back then this guy said something about that. I think the key point is going to be that, I mean, I've never started a company, developed engineering, I've never done this kind of thing myself, but if I imagine how I would go about it, you're going to have to be really site-specific. It's like finding mines on Earth, right? And of course, we're the only people who understand that as geologists. We have to explain to the scientists and the engineers, you know, a tremendous amount of science goes into finding and explaining a gold mine, for example. That's why we're here. The same kind of stuff is going to happen on the moon about finding your gold mine of where you can most optimally build your structures. Now, whether that influences the site selection, whether it will be changed in the future, whether there are wise people already talking about it, I don't think there are, I don't know. But I can imagine that some sites will be abandoned and other sites will be created. This all lies in the future now. It's like Europeans coming to America. You're going to make a lot of mistakes, not just because of the indigenous people, but also because of where you went and what you did. Going to be a lot of failed colonies, I suspect, on the moon. And, you know, it's only geoscientists who are going to have the patience and the wisdom and the experience to tell them exactly what these local materials mean and how they're going to behave. That's the business for you guys. That's the business for mineralogy and petrology and all of this. It's a wonderful opportunity. But we have to tell them. Again and again and again. That's what we always have to do it several times.
Okay, thank you very much for your talk.